Okay, let's start. Good morning, afternoon, and evening. Hola, hello, bonjour, hola. Ni hao, konnichiwa, 안녕하세요. And hello all. Welcome and thank you, SynBYSS people, for joining us, the 117th seminar, and I call it a Ruhr University Day, Germany. 11 days ago, I was exchanging multiple emails at around, I believe, 1:30 a.m. in the morning with a professor in Israel at the time. We were scheduling a Zoom meeting time, but he was confused because he just arrived there. I'm talking about Israel from the United States, and he was kindly letting me know his availability in my US Central Time. At the time, I did daydreaming or morning dreaming, imagining what if we have only one official time with sunrise and sunset times identical in the entire globe, although it is impossible. Today, we have two amazing speakers from Germany and Korea with inconvenient time zones for speaking today, especially Korea, where the time is right now midnight and it will be past 1 a.m. later on today. A good thing or confusing thing is the USA right now follows daylight saving, meaning it could be 1 a.m. in Korea, where Koreans do not have daylight saving if we started this seminar a bit, several days ago. A more confusing thing is that even nations that have daylight saving start their summertime at different dates. I wondered whether we could have one clock, although diversity or complexity is one of the beautiful things in life. One good thing nowadays is that internet or smartphone tell us local time. I have traveled so many times and so many days and so many places, more than 300 days for the last 2 years. And those technologies, in fact, save my days. Okay, it is my tremendous honor to introduce very briefly. I tried to brief, but probably that's impossible for me to do so. Our pioneer speaker, Professor Dirk Tischler. He is a professor at Ruhr University in Bochum, Germany. I got to know him for the first time, I believe, in 2021 when I started to use social media for the first time. And then he kindly invited me to his institute by supporting all trip costs, including air ticket from United States to Germany, hotel, and most importantly, food he cooked himself. Wow. It was really, really enjoyable visit, thanks to great scientific discussions and his hospitality, and of course, the amazing food he created with his lab member. And now we are organizing together the first SynBYSS conference in Hawaii. He is also helping me as an editorial board member of New Biotechnology, where I serve as the editor-in-chief. However, he's not helping my weight control effort because it became my weekend morning habit to see his social media photos of his amazing weekend lunch cooking and the food. Because of time difference, I always see that in the morning That is basically his lunch time. A good thing is that I was a terrible cook, horrible cook, who used to use only frozen food, but he inspired me very much, making me cook recently. So Dirk, I wanted to do short introduction, but it was impossible. So Dirk, thank you so much for your so many contribution to my life and the community, and the virtual podium is all yours now. Thank you so much again.
Thank you for the introduction. So let's share the screen. Okay. So I hope you can see the screen.
Yes.
And then I give you a short appetizer, as you like food, on what we are doing. And it's basically research on actinobacteria most of the time, and we use them as a source of biocatalytic tools. So why actinobacteria? Or I could actually say we are focusing on Rhodococcus and Gordonia. And the explanation is very simple, because when I was a student, and that's quite some time ago already, I read those articles where it stated that the Gordonia is metabolic diverse, or Rhodococcus is the catabolic powerhouse. And I really love those articles, and I got intrigued by those. And when I then finished my PhD thesis on a flavoprotein, I saw this article, and it was basically an article about biovilica monooxygenases, which are also flavoproteins, and the study is about the same organism as you can see here, this Rhodococcus RHA1, and it has way more than 20 biovilica monooxygenases, and yeah, so I stick to that, actinobacteria, mainly Rhodococcus, actinobacteria, and flavoproteins. And so I intrigued my group actually to work on the same topic. So without those young enthusiastic people, you cannot present here. So I'm happy to have this group. And as Tisa said, we are cooking many times together, so we enjoy a lot science and food. But what we are doing, for example, work on the azodai degradation. Azodais, you all know, they are in textiles, in food, in cosmetics. But when it comes to degradation, also so simple compounds like methylred, for example, they end up most of the time in aromatic amines, and they can be toxic. But you can get rid of those by cells or enzymes. We have way more than 100 strains in the lab and screen them for the degradation of those compounds in various formats. You can see here the plates, and yeah, the strains are just growing on these dyes. Even complex dyes, as you can see here, the chlorzo black is used, biosorbed and also degraded. The simple compounds you have seen before, methylred, that's just used by some of our strains like glucose. So they basically grow on that. But the inspiring thing for the moment, we don't know yet pathways, enzymes which are involved. So there's still a lot to do. Another topic can be lignin degradation in my lab. So another complex compound, which is also a natural source of aromatic compounds. And we can fuel it to our cell factory, which is indeed the Rhodococcus again, and produce very interesting compounds. And if you have a closer look, those aromatic compounds you can fuel into the central metabolism of Rhodococcus. That's all known. And then you can actually introduce a knockout and decouple growth substrates and production substrates. So that's a common strategy, I would say. And without a lot of manipulation, you can make use of Rhodococcus and produce already a little bit of ferulic acid. So we found a bottleneck in this pathway, which is the initial enzyme, this called HUGO. It's a eugenol oxidase. It accepts rather small substrates. If you want to have bigger substrates or larger aromatic accepted, you have to change it. So we were screening for those. Here we employ most of the time phylogenetic studies, and we found and by a computational approach, an enzyme which is from a Streptomyces, so another actinomycete, which can accept bulky substrates. We got the structure from that, and then we screen for activity, and indeed, the Streptomyces enzyme can accept bulky substrates. So this you can then also see in the structure when you get the substrate docked in. So that's quite nice. And the next step, which is future research not done yet, so we have to bring this enzyme back to Rhodococcus and apply it in our cell factory. Another topic we are working on is another aromatic, that's styrene. Most of you probably know the monomer for polystyrene, but we could ask ourselves about pathways. But from a biocatalytic point of view, we can also ask the question in a different way. So can we produce ibuprofen, for example? So from a biotechnology point of view, that's very simple. So you know pathways, enzymes, so you put them in a box, that's your cell, and produce ibuprofen. What we know is that if you feed styrene, you can produce phenylacetic acid, and this is quite similar to ibuprofen. So if you change the substrate a little bit, you should be able to produce ibuprofen. And indeed, by screening our strains, we found actinobacteria which do so. But interestingly, only 1 out of 60 strains does. So that was strange to us because we thought, yeah, all our styrene degraders should do that. So we found actually out in a quite, let's say, elaborate study that the normal styrene degradation pathway, which you see on top, cannot yield ibuprofen. But if you have a more complex pathway shown on the bottom, which uses actually glutathione and the glutathione S transferase, then you can produce ibuprofen. And that's another interesting feature because glutathione is not really abundant in actinobacteria. You hardly find it. But for this pathway, it's possible to be employed, and it is the important step to get to ibuprofen. At the moment, we are struggling a little bit with this pathway because we don't know where the glutathione goes out again of the pathway. So there's still work to be done. But what is interesting, if you compare the styrene degradation pathway with glutathione S transferases, you have a similar thing in other strains, which are Rhodococcus, for example, which you create isoprene. And this is more or less the same set of pattern of enzymes reacting there. And it's quite interesting. There are only a few actinobacteria, if you look in all the genomes, which have glutathione S transferases, and they're mostly in those pathways which are related to styrene or isoprene of soil bacteria, I would say. Another interesting feature of this special enzyme, this glutathione S transferase, is that you can employ it in biocatalysis. So because it's enantioselective, you can use it for kinetic racemic resolution. And here we're preparing another paper. So if you're interested in combining metabolism and application, this is a nice enzyme. And if you further want to manipulate those strains, so that's also a recent project we started. We want to have all our actinobacteria, just a list of few of them, and engineer them. And a genetic toolbox, in our case, should be a uniform protocol, so simple to handle, simple to manipulate. And I can show you can easily produce, for example, GFP with our strains. You get decent yields, but more important, if you work with actinobacteria, you have to break at the end the cells if you want to get hands on the enzymes. And you can use sonication, that works to some extent. You can use a fluidizer, which is similar to French press somewhat. It's not really working. You see most of the protein still in the pellet, so you don't break cells. And the constant system we also have in the lab, that works quite nice. So it really opens the actinobacteria and you have access. And you can also compare it to conventional systems. So like E. coli, if you just look at the bottom line, we expressed in E. coli the GFP and got a decent yield comparable to our Rhodococcus strains. But one of our Rhodococcus strains, actually one of my pets, the 1CP, produces up to 3 times more GFP than E. coli. So they are quite valuable organisms. So, and with that, I'm more or less at the end and give you my take-home message. So actinobacteria are really cool. So they degrade all kinds of compounds. They grow on everything, basically. They can produce interesting natural products. We're also working on siderophores, trehalose lipids, and those kind of things. You can use them to study host microbe interactions. That's quite nice. You don't have to work with nasty mycobacteria, but can work with Rhodococcus if you want. And in our case, we most of the time use it at the end also as a source for biocatalysis. And as you know, there are processes like the production of nicotinamide or acrylamide out there at the ton scale, and we hope to contribute in this direction as well. And with that, I'm at the end, have to thank some sponsors and thank you for your attention.
Thank you so much. Amazing talk. You remind me of my first research 27 years ago. I used Streptomyces to produce antibiotics. That was so hard because at the time, not that many genetic tools available. This gram-positive bacteria is super challenging to work with. And then at that time, I promised to myself I never work with the actinomyces, actinobacteria, whatever. And then now I start my position, and then I start with the rhodococcus somehow. I don't know why, but that is something fun because I don't need to deal with daily problem every day because that my student working hard to make me do that research. So, and then you show at the beginning the Linz LTIS paper, that's beautiful paper, that inspired me as well. And
Yeah.
one day I hope not only you fermented beer or wine, I hope you make bacteria produce your amazing meat or sausage, whatever, one day, I want to see that happening in the future. So brilliant. Thank you so much.
Thanks.
All right. So now the main speaker of today with a longer introduction, Dr. Taehee Han is a postdoctoral researcher at Korea Advanced Institute of Science and Technology. You probably know that as KAIST, under the guidance of her advisor, Professor Sang-Hyuk Lee, one of the most famous metabolic engineer or systems biologist. She earned her bachelor degree and PhD degree at KAIST, the best technology university in Korea. Her research focus during her PhD training encompassed metabolic engineering, synthetic biology, and microbiology. Notably, she actively engaged in the development of bio-based method for the production of monomers used in polymer synthesis. Her dedication to this field led to many publications focusing on microbial production of various monomers for plastics and nylon. She also worked for developing a synthetic small RNA tool. Actually, that's one of my favorite papers published in Sang-Hyuk Lee's lab, facilitating the efficient construction of platform substrates. Currently, she is still actively working on metabolic engineering and synthetic biology research, and also is always eager to explore new research opportunities, including omics analysis as well. I believe she and I met for the first time when I was visiting KAIST to give a seminar, and then recently when I attended Metabolic Engineering 15 in Singapore that I co-chair with Matthew Chang and others. She also helped me by kindly serving as a reviewer for one of my 9 journals where I am serving as an editor. She will soon be embarking on a new journey, joining Professor Harris Wang's lab at Columbia University to explore additional fields in biology. Taehee, thank you so much for joining us at the very inconvenient time, I mean after midnight, and please take it away. It's all yours now. Thank you.
Great. Thank you. I'll share my slides. You guys see my slides?
Yes. Wonderful. Thank
Okay.
you.
Great. So yeah, thank you very much for the kind introduction, Professor Moon, and thank you so much for the great talk, Professor Tischler. Right. I'm really happy to be here today, and thank you again for this great opportunity to present my work. So this is just an introduction page of me. And as Professor Moon already introduced, I got my bachelor's and a PhD degree in KAIST and under the guidance of Professor Sang-Yep Lee. So my research has been mostly focusing on metabolic engineering and synthetic biology. So today I'm going to talk about some of the works I've done during my PhD, which is titled as Systems Metabolic Engineering for the Production of Monomers for Polymer Synthesis. So before we dive into the details, I will let me give you a brief introduction what systems metabolic engineering is. Although I guess most of you already know. So systems metabolic engineering is an integration of the field of metabolic engineering, systems biology, and synthetic biology to optimize the performance of microbial strains for the production of valuable chemicals. So for many years, with the advancement of various metabolic engineering technologies, the development of microbial strains for the production of wide range of substances for across various fields has been achieved. So among them, most of my research focused on using the bacteria called Corynebacterium glutamicum. This amazing microorganism has several advantages, such as being non-pathogenic, and its products can be widely used, generally recognized as safe. And it has been actually already been using for some industrially important compounds, not limited to amino acids. So what I aim for using this organism and systems metabolic engineering strategies was to contribute to this polymer industry. So it's already a massive market with expectations of substantial growth in the future. And within this industry, polyamides and polyesters possess a significant portion. And for their synthesis, there are amide carboxylic acid and diols as monomers. Actually, so currently most of them are synthesized through petrochemical industry. So my goal here was to apply systems metabolic engineering for the production of these monomers, and specifically lactam, glutaric acid, and 1,3-propanediol from its category. So let's start with the first topic on glutaric acid production. So glutaric acid of 5 carbon dicarboxylic acid serve as a platform chemical for diverse applications in the polymer industry. So first, we began to find some natural pathways for the glutaric acid production, and we chose this promising route starting from lysine, one of the well-known amino acids. The reason why I chose this pathway was that we used to have this lysine overproducing Corynebacterium glutamicum strain, which is called as BE here, which can produce lysine up to like 20 grams per liter in the glass cultivation. This actually is amazing ability. So we wanted to use this advantage for the high level production of glutaric acid. So the figure here in the lab shows a pathway all the way from glucose to lysine and lysine to glutaric acid. But the problem here was that Corynebacterium lacks the pathway from lysine to 5-aminovaleric acids, which is an important intermediate in the glutaric acid biosynthesis. So to address this, we created some various plasmid combinations for overexpressing these 2 foreign genes from Pseudomonas putida in the 2 native genes, GAPT and GAPD genes of Corynebacterium. So after testing multiple combinations, we found that using this PGA4 plasmid led to the highest glutaric acid production. And then we further assessed the performance of this strain by the fat batch fermentation, and it produced 54.4 grams per liter of glutaric acid successfully. And then we aim to boost the flux of this glutaric acid production. So I introduced some metabolic engineerings, which are already known to increase the lysine flux into the genome of the host strain. But sadly, these rational engineerings failed to enhance the lysine flux in the study. So at the time, I was kind of depressed because it took me some months to introduce all these genome engineerings, but none of them was effective. But I hypothesized that this was because of the differences between the wild-type Corynebacterium and the BE strain we are using for this study. So to tackle this challenge, I conducted a multi-omics analysis, including genome, fluxome, and transcriptome for this BE strain. So first thing I did was the whole genome sequencing of this BE strain. And then we reconstructed the genome scale metabolic model by the help of Dr. Ki-bae Kim in our lab. And then using this model, we proceeded two different fluxome analysis for identifying some novel targets to be engineered for increasing the glutaric acid flux. And later, I also performed this comparative transcriptome analysis to compare the gene expression profiles of the wild-type Corynebacterium and the BE strain. So by combining all the analysis results from this multi-omics analysis, we could not only understand our BE strain metabolism, but also could identify some new 11 target genes as manipulation targets for the increased glutaric acid flux. So we actually introduced all these genetic modifications into the BE strain genome, and it resulted in the creation of GA16 strain, which produced this amount of glutaric acid, which is approximately like 2 times more glutaric acid than the control strain. This kind of results show that the multi-omics approach done here was very effective for such metabolic engineering studies. And then after some optimization of the fat-based fermentation conditions, we achieved a final glutaric acid titer up to like 90.5 gram per liter. And this was already a big number at the time, but we kind of wanted to increase the number a little more, like to a 3 digits number. So for that, what the last thing we did was the identification of a novel glutaric acid exporter. So this transporter engineering is also an important part for creating an efficient microbial cell factories, because we always want the cell to pump the desired chemical out for the higher yield and higher productivity. But at the time, there was no known glutaric acid transporter gene. So I searched for some databases and created this 8 different candidate genes for the overexpression. And here, as you can see, this number 5 genes, which is YNFM gene, show the most promising glutaric results, increasing in the glutaric acid production by around like 30%. So this was identified as a new glutaric acid exporter, and we also filed a patent about this. And having confirmed this effect of exporter engineering, we replaced the native promoter of this YNFM gene into a stronger one in the genome. And this final GA17 strain achieved the highest of glutaric acid titer of 9.4 gram per liter in the flask cultivation. Then we further tested the performance of this GA17 strain by fat-based fermentation, and it achieved 105.3 gram per liter of glutaric acid production in just like 69 hours, which was remarkable. This represents the highest titer updated to date, and there was no byproduct at all other than the desired chemical, which will be a great advantage for the downstream process. So later, we also purified this bio-based glutaric acid with the help of Dr. Dong-Eun and we also confirmed that this was exactly the same as the commercial glutaric acid standard. So with that, I could complete this glutaric acid project, and this was personally published in PNAS, showing the advancement in bio-based glutaric acid production. Okay, now moving on to the next chapter, I would like to present the work on amide production, specifically a lactam production. So here, lactam is a ring-shaped amide compound used for the synthesis of various nylons. So especially nylon 5 and nylon 6 has some good characteristics. So there has been always demand for the production of these monomers. But however, microbial production of these lactams has been relatively limited. And previously, our lab created this E. coli strain capable of producing like various carbon numbers of lactams. But still, as you can see, the titers reported here were quite low. So we started to create a new platform strain for the high-level lactam production. So having the lysine overproducing strain I introduced earlier, we thought that this strain also has some potential to produce this phospholactam through this lysine-derived pathway. So in the same manner as the first chapter, we designed and constructed a phospholactam biosynthesis pathway by introducing some foreign genes from Pseudomonas butida and Clostridium propionicum. So the first step involves converting lysine to a 5-amino valeric acid. And then the second step transforms this ABA into a ring-shaped phospholactam. So through fine-tuning some various gene combinations, we successfully conformed the phospholactam production in the Corynebacterium glutamicum strain. And then for the next step, we needed to increase this phospholactam flux in the host strain. So one strategy here we used, it was the application of the sRNA system for identifying some additional genome engineering targets. So I assume that most of you already know that how the system works, but let me briefly explain the mechanism. So when we introduce this sRNA system into the cell, the small RNA goes to the translation region of the targeted RNA. Then the ribosome cannot bind to the region, which will be resulted in as a repression of this target gene. So our lab has recently developed the system to be applicable to diverse gram-positive microorganisms. So we decided to use the system for this study as well. So here we constructed a sRNA library targeting 12 genes in Corynebacterium glutamicum and tested their effects by introducing them into the phospholactam producing strain. And from this result, we could get 3 different genes target, which leads to the increase in phospholactam production. So next, we downregulated these 3 genes in the genome level, and the resultant VL5 strain showed higher performance in producing phospholactam up to 42.8 grams per liter by the fed batch fermentation. This was already a highest number at that time, but we found that there was a big challenge in this result. As you can see in the graph, there was a significant amount of 5-ABA, which is an intermediate compound in the phospholactam pathway. So to address this issue, what we did for the next step was the transporter engineering. So we hypothesized that keeping this intermediate molecule in the cell would facilitate the phospholactam flux. So we created a list of 5 putative genes from the databases, and each of these genes were subjected to either overexpression or deletion, allowing us to evaluate their effects on 5-ABA production. So among the candidates, we could get this NCGAL0464 gene as a 5-ABA importer gene responsible for the reuptake of FABA back into the cell. So having this result confirmed, we enhanced the expression of this gene in the genome, and we confirmed that the reduced 5-ABA amount was indeed redirected toward phospholactam production. But however, as you can see here, there was still some amount of 5-ABA remained. So the solution came up in my mind at the time to solve this issue was to simply increase the flux from 5-ABA to phospholactam by introducing multiple copies of these ACT gene, which is responsible for this reaction. So as you can see here in the graph, as we introduce this ICT gene in the genome, the 5-ABA remaining is reduced, and that much of phospholactam production has increased. And the final strain in this series of VL9 was created, and in the fed batch fermentation, this strain achieved 64.4 grams per liter of phospholactam production, which is a high increase, and there was no 5-ABA anymore. And then as a last step, we focused on strengthening the glucose uptake system. So the current Corynebacterium glutamicum is highly dependent on PTS dependent glucose uptake system as a main source. But from the previous studies, it has already known that if you increase this PTS independent system as well, the production will be increased. So we introduced this genome engineering, and the final strain of VL10 successfully produced 9.68 gram per liter of alpha-lactam in flask. So this was about like 5-fold increase compared to the control strain, which means that the metabolic engineering strategies we have done so far is very effective. And then we finally tested the performance of the VL10 strain in the fat batch fermentation, and we achieved this 76.1 gram per liter of alpha-lactam production without any other byproducts. And this record represents the highest titer productivity and yield out to date. So this was how I completed this lactam production project. And we recently published 2 research papers last year as a result. Then finally, the last chapter is about the production of diol, specifically 1,2-propanediol. So this project was kind of special because we did this project with one of the representative chemical industry in South Korea called Hanwha Solutions. And we have done this with this many people for like 7 years. So in fact, most of the experimental results are kind of confidential because it's a company project. But today I will just briefly talk about the concept and the main strategies that we used. So one day, this Hanwha Solution guys came to us and asked us like to find some targets to convert this crude glycol, which is the bio waste from this biodiesel industry, to something valuable. So and here we decided to produce 1,2-propanediol, which has a wide range of applications in the polymer industry. So currently, this 1,2-PDO is produced by petrochemical waste, including some toxic materials and high temperature conditions. So to make it to a bio-based 1,2-PDO production, we designed a new synthetic pathway toward 1,2-PDO from glycerol, as shown in the figure. But for this, there were some big challenges. So the first thing was the Corynebacterium does not consume glycerol as a natural carbon source. And then the second one was that this 1,2-PDO biosynthesis pathway does not exist in this organism. So to make a long story short, this one page summarizes how we developed this industrially relevant 1,2-PDO producing microbial cell factory from the scratch, which actually took us more about 7 years. But actually, there are so many experiments behind to make this goal come true. But sadly, I cannot share the detailed strategy today. But we are actually planning to publish a paper soon, so you will find the details later if you are interested in. But anyway, from this project, we could record the world's highest 1,2-PDO titer yield and using a novel biosynthesis pathway. And we also succeeded in constructing an economically competitive microbial cell factory. So this actually was a great opportunity for me to learn how companies work and what they really want when they are bringing metabolic engineering to an actual industry. So to recap, the ultimate goal of my research was to contribute to a polymer industry using systems metabolic engineering. So far, I briefly introduced the metabolic engineering strategies I use for the production of each of these chemicals, like valuable monomers. And for each chapter, I could successfully create efficient microbial cell factories with some outstanding performances. So by that, I could prove the systems metabolic engineering here can convert biomasses to something very important chemicals. And further, I believe that this will opening the way for the eco-friendly and sustainable bioindustry for a variety of chemicals, not limited to polymer. Okay, so I would like to express my gratitude for the support and all the guidance I received from Professor Sang-Yeop Lee and all the lab members and co-workers who helped me a lot. Okay, that was all for my presentation today, and I hope you found it interesting, and I'd be happy to take any questions. Thank you.
Amazing talk, amazing talk. Absolutely brilliant. I also believe your first paper reviewed by me, the PNAS, right? The first.
Yes, right.
Yeah, I remember that one. That's amazing, the paper. So I really like it. Dirk, I have some question, but I want to give you opportunity to comment or ask question first, and then I will ask some typical challenging question later on.
Yeah, wonderful talk. I have a very simple question. When you start manipulating strains and optimizing pathways, what are you doing when you enter like a plateau and the evolution is going, let's say, further and you not improve anymore?
You mean when the product is not like improve anymore?
Yeah.
What am I do? What do I do? So there must be a bottleneck for in the case of production always, right? So we try to find what the bottleneck is in the biosynthesis pathway. So sometimes it could be a toxic chemical that is like harmful for the cell growth or something. And sometimes the flux itself from the intermediate to the desired chemical is not enough to pull that all to the desired chemical. So we try to find in this way the bottleneck, what the bottleneck is, and then to resolve this problem to increase the flux toward the target chemical.
Dirk, do you have any other question?
I could have many questions.
So go ahead.
I mean, grüne bacterium, that's a nice strain. It's really a nice model organism. Many people in Germany work on this as well.
Yeah, right.
And I think the lysine overproduction is a good starting point, what you said, to go to valuable compounds. Are you considering also in other directions, so not just lysine as a starting point?
Actually, like most of my research was focused on chemicals based on lysine. But hopefully I'll be explore more fields later on.
Yeah. Because you could imagine that other amino acids, which also can be overproduced by corona, can be nice starting point too.
That's right. Right.
Any other, Dirk?
No, for the moment not.
Okay, so let me ask question. So now you are a little bit transitioning from metabolic engineering to potentially microbiome. So, but I still want to ask that question because you may come back, when you become a professor, you're probably going to combine two expertise you learn from Professor Sang-Yeop Lee's lab and Harris Wang's lab. So
Yeah.
I'm going to ask big question because I know your work very well, including the paper, PNS paper I review. So my question is a very big question. I even asked that question to Professor J. Kisling, also I believe Sang-Yeop Lee, Professor Sang-Yeop Lee, and also probably Greg Stephanopoulos. So if you don't have answer, don't be, disappointed because it's a big question. So, metabolic engineering, I believe started, 1990. So that is, now, more than 30 years ago. The metabolic engineering improved, progress a lot. And we now have multiple tools like prediction tool for the flux, genome scale model. And also we have some protein engineering tool like AlphaFold to improve the enzyme. We also use the directed evolution, to improve some enzyme. Also systems approach, that is a Professor Sang-Yeoli's expertise, kind of regulate individual enzyme, but large scale. So we have all the tool now, a lot of tools. But compare, basically it's the same line Dirk already mentioned, how to improve further, because we are not reaching the theoretical year or whatever, theoretical, most of time, sometimes we reach that point, but most of time we are not reaching that one. And then to go there, including your last example, 7 years of a lot of money, a lot of people. So my question was, also is to you, I'm doing metabolic engineering now more than 10 years, probably almost 20 years. I still feel like I'm doing art rather than engineering. Because we tackle one problem and then move on to next project. And then we use the same tools, but not necessarily same tool work. Some tool work, but some tool probably not working. So can you share your insight or perspective, how to make my feeling I'm doing art rather than engineering to become the next step that is a real engineering. I'm talking about real engineering means real programmable, real predictable. We know which enzyme we should target without doing any random screening. How can we go there next 10 years? That's my question. This is a big question. J.K. Jennings gave very interesting answer. Greg gave very interesting answer. Professor Sang-Yeoli also gave very interesting answer, but I just want to hear from you.
Okay, that's a great question. I like that. But at the same, it's a tough question. So in my opinion, maybe it's the time for adapting the AI, like artificial intelligence, in this field, like more actively, so that we have been using all the like manual engineerings and rational engineerings, and even some like random screening or random mutations kind of thing. It was like more developed than the like previous manual strategies, but still it's kind of limited to actually understand and fine tune all the steps in the metabolic engineering field. But if you use this artificial intelligence or some computer tools, I think we could go beyond the stage of the metabolic engineering of now. So that'll be a big step change for our field. And at the same time, while I was doing this like company project, I could feel that this was not like the lab scale research anymore, and it's kind of really applicable to a real industry which can make some profits in the future. So I think that this kind of experiences, although it kind of fails in the end, so working with a company or some making a startup to make a profit from what we have developed in this metabolic engineering field would also give some more insights which we never had before. Yeah, that was my answer.
That is excellent answer. So you touch very important 2 points. One of them is basically using computer AI. Even though that's now hot, I believe in the future, we probably need to develop a lot to make that really happening, because some of the organism product, we have a lot of data, so we could use machine learning AI to achieve that goal. But some of the products and also some of the species, we don't have much data to use machine learning, but we should have some other way to deal with that problem. And the second thing is more important. You mentioned now it's time to deliver real product, not only just the 1-3% propandiol that's already commercialized, and some other product we already commercialized, but we need to have more, much more than what we currently have. In that way, we could deliver and then prove biomanufacturing is a real thing rather than fancy, trendy word. In that way, we could basically make the field moving forward. So absolutely brilliant answer. I probably like more than other answers I had. I mean, one of the great answer from Jay Kiesling, he made a joke saying, "Do you think I am an artist?" And then he started to explain his perspective. That's a brilliant answer anyway, but he started with the joke. But yeah, I mean, we could become the real engineer in the future, incorporating all of the things you just mentioned, and also all the things the other pioneers already kind of share with us. Wonderful. Dirk, one last time, chance if you have any further question or comment.
Yeah, I was thinking about the same question now, and maybe a point can be if you think about from an organic synthesis point of view. So there we have the concept of retrosynthesis. Can we not employ the same in metabolic engineering and then using AI to combine let's say AI to decide to select which enzyme, which promoter, which regulation, which export system you're going to use. So that would be a nice combination, and actually all the tools should be there already.
Yeah, absolutely. Actually, you know what? My PhD thesis project with the Christina brother was all about retrobiosynthesis. So basically, we rely on organic chemistry concept. So starting from not starting from the substrate, we start from the product, and then thinking about backward, what is the precursor for making that product, and then we kind of all the way to whatever feedstock. And then what at that time I thinking about, okay, can we just predict which enzyme might be the best without searching hundred of enzyme or screening hundred of enzyme? Can program or computer predict this is the enzyme I need to use, this is the promoter strength I need to use, this is the RBS strength I need to use? By that I mean the engineering. Right now we generate library, screen the best one that takes one PhD thesis, 4 years, 5 years. But we are going there. And then as you mentioned, we also not only the pathway itself, retrobiosynthesis, we need to engineer the strain as well to get rid of all the side effect, side reaction, whatsoever. So that's a not easy problem. And then one thing I remember from Jay Kiesling's answer, he said biology is still messy, too complicated. So biology is messy and we need to understand more, but we are getting there. So I'm hopeful and optimistic because the people like the Taehee Han will address and solve the problem, let's say that's next 10 years from now. So that is what I hope.
So you got a task now.
Any other thing?
Yeah,
Otherwise,
for Corynebacterium, it's also interesting because there are minimal genomes around. So are those strains also, let's say, vital enough for a cell factory, or they are problematic? Because then you avoid some of the pathways to side products and so on.
There are so many advantages of using Corynebacterium for the industrial scale or bioindustry. Like, for example, it's kind of very strong. So usually a contamination is a very important factor and a big problem when you use this microbiome, microorganisms for the industry, biomanufacturing. But Corynebacterium is like rarely contaminated. It itself is really stronger than other microorganisms, so it's really easy to handle for some manufacturing. And secondly, it grows very well at 30 degrees Celsius, whereas the E. coli, which is a very well-known bacteria, is grown at 37 degrees. And I heard that for the biomanufacturing, consistent temperature and then keeping this like high temperature costs a lot of money, but 30 degrees is cost like less money to maintain the temperature. So it's kind of another advantage of that. And currently, there is already a lot of like tools for manipulating all the genomes, like such as CRISPR or an sRNA for this organism. Otherwise, but for different from other kind of actinobacteria or rhodococcus, where there's not many tools to engineer them, right? So that point is also a good advantage for using Corynebacterium.
So that's interesting. You said the Corynebacterium is less prone to the contamination. Is it because of they generating a lot of solvent compound, or why is that?
Actually, it's not producing a lot of solvent, but it's first it's a gram-positive bacteria. I think it kind of affects to a rigidity up the strain, and it grows really well and it grows very fast. So it's like already if we grow some bacteria together with Corynebacterium, it already grows so much faster and so much than other bacteria. So the other bacteria cannot grow when a Corynebacterium is nearby. So I think that's
even including E. coli.
Yes.
Or even E. coli grow. I mean, but to me, E. coli grow faster than Corynebacterium, right?
Yeah, I mean the doubling time kind of thing is like shorter for in case of E. coli, but it's kind of more strong. So if you grow together, E. coli is vulnerable to contamination, but Corynebacterium never be contaminated.
Interesting.
Yeah. So for example, our lab kind of had a problem. Like one time, there was kind of a fudge contamination in the lab. It was a very big problem because all the E. coli strains we were using all died in the middle, and all the flask cultivation didn't go well because of this fudge contamination. But only Corynebacterium, the people who were dealing with Corynebacterium were happy because they were not dying at the time. So
you're talking about the bacteriophage.
Yes, phage.
Oh, so in that case, I mean, you're talking about bacteriophage contamination, not the bacteria contamination. Because to me,
yeah,
that is a beneficial. Yeah, of course, I mean, phage is a big problem in big scale fermentation, large scale fermentation. So if that is the case, then I understand. But I believe that if you grow Corynebacterium and E. coli, probably E. coli also, contaminate for sure. The phage problem is different one because E. coli typically killed by phage very easily. So that's another problem for the big fermenter, scale, production. But that's interesting. One last question, quick question. How many -80 refrigerator, freezer do you have in the lab? Probably you have many, right?
We do have a lot of deep freezers. I cannot remember the exact number, but I bet we have more like about 10-ish.
Oh my goodness. So
Because
that means
we've been creating all the like microbial strains for like 30 years in this lab. So but there's a lot of strains. Yes.
Yeah, I was always curious. I mean, that one. So thank you. Yeah, okay. Thank you. So we probably close because I should let her sleep soon. Okay. So thank you all for joining and staying today. We'll meet again on March 21, Thursday, the same time, the same Zoom link. We'll have Dr. Jermont Chan, a program manager or director at NIH, and also Professor Caleb Basho at Rice University. As usual, the follow informal chat will occur without recording. Please stay here if you are interested in chatting with us. And thanks again. I will stop recording. Just give me 1 second.